welcome you back to Winkle's class once again. Today's video marks the continuation of the series of videos that I promised you, and also it represents the third episode of understanding UV visible spectroscopy. So before we jump into today's content proper, let me remind you of the importance of your subscription. Please don't forget to subscribe to the channel because it is very important and it will help the channel grow. And also don't forget to like the videos and then share with your friends as well. Thank you very much. Now let's jump right into today's content. Electronic transitions that are observed in UV spectroscopy. That is what today's video is specifically about. So, for the objectives of today's video, let's look at the things that we are going to capture in today's content. We are going to talk about HOMO-LUMO electronic transitions. We want to know what HOMO and LUMO electronic transitions are and then how they usually occur. Okay, and then we'll also talk about some major organic functional groups and then their respective electronic transitions. So for example, when you talk about alkanes, alkenes, carbonyl groups, what are the specific electronic transitions that will help you identify them in a particular sample? That is what we are going to talk about in this particular video. And also we'll look at the explanation or the meaning of far UV, vacuum UV, and near UV. When you hear these terms, what do they convey to you? What does it mean? When someone tells you that this particular wavelength or this particular radiation is in the far UV column, what does it mean? That is what we are going to look at as well. And also we'll look at some electronic transitions and why some are observed and why some are not observed. You know, several electronic transitions can occur, but then it is not all of them that are observable. You might be able to observe some of them and then some of them you wouldn't be able to observe them. We want to know the reason behind that. Yeah, so these are the objectives for today's video, and not to waste much time, let's jump right into the main content. So we'll talk about HOMO to LUMO electronic transitions as the first thing. When we talk about HOMO to LUMO transition, HOMO simply means highest occupied molecular orbitals. Alright, so if you follow the cursor as you usually do it, the diagram below the slide, okay, follow the cursor very well. When we talk about highest occupied molecular orbitals, looking at the molecular orbital diagram, okay, there are several aspects. As I did in the first episode of the series of videos that I am releasing, you realize that I explained that we have bonding molecular orbitals and we also have non-bonding molecular orbitals and we have an anti-bonding molecular orbital. Yeah, so following that understanding, okay, if you don't understand it, or if you failed to watch the first episode of this season, I would plead with you that you go and watch it so that you can get the major understanding that will drive you through this particular content, because the series of videos that I'm releasing is kind of like a build-up. Yes, so it will be advisable for you to start from the beginning and watch step by step in order to understand it very well. Yeah, I would put the link to the first and then the second episode of the series of videos in the description box. That is, when you need it, you can just just click on the link and then it will take you to the videos. All right, now let's come back to the main thing. So as I said, when you take this molecular orbital diagram, there are several parts of it. We have the bonding molecular orbitals, which is the pi and then the sigma, okay, and we also have the non-bonding molecular orbital, which is the n here. This is where lone pairs of electrons occupy. Electrons that did not take part in any kind of bonding, this is where they occupy. And we talk about the anti-bonding or the anti-bonding molecular orbitals, and this is where they are, the pi star and then the sigma star, as I explained very well in the first episode. Yeah, so you remember that I also said that for the bonding molecular orbitals, there is a very high probability of finding electrons in between the two nuclei that are combining. So for example, if this atomic orbital 1 is combining with this atomic orbital 2, when you combine these two, that is where you got these molecular orbitals. All the molecular orbitals here were obtained from the combination of this atomic orbital and this atomic orbital, right? So I said that when you combine two atomic orbitals in order to form a molecular orbital, when you combine them constructively, okay, when the combination or the interference occurs constructively, we'll end up forming a bonding molecular orbital, which is either sigma or pi, depending on how the overlap occurs. If it is side by side, it will be pi. If it is head on, it will be what? Sigma, right? Good. So based on that understanding, if you want to know, okay, which orbital is HOMO and which one is LUMO, you need to be able to keep that understanding in mind. Bear it in mind that the pi and then the sigma orbitals or molecular orbitals are usually occupied. Okay, they are usually occupied. Why? Because there is a very high probability of finding electrons in between the nuclei that are combining. As I said earlier on, the the interaction is constructive, right? And if it is a constructive interaction or a constructive interference, then it means that there is a very high probability of us finding electrons in between the two nuclei that are combined. Yeah. So usually we call this molecular orbitals, the bonding molecular orbitals, are occupied levels or occupied orbitals. Why? Because we expect them to always be occupied with electrons. The non-bonding molecular orbital is also included in the occupied levels because usually we expect to find electrons on it, electrons that are lone pair, like electrons that have not taken part in any kind of bonding, right? Electrons that are left unbonded, let me say it that way. Yeah, so they are the ones that occupy this place. So because there is also slightly high probability of we finding such electrons when we are dealing with the formation of bonds, we also include the non-bonding molecular orbital as part of the occupied orbitals. All right. Then for the anti-bonding orbital, which is the pi and the sigma star, as I said earlier on, for you to form an anti-bonding molecular orbital, it means that the two atomic orbitals are combining destructively in a sense that there is a very low probability of you finding electrons in between the two nuclei that are combining. Yeah, so usually because of that, we usually refer to these levels as unoccupied levels, because we don't expect to find electrons here unless an electron transition occurs or an electronic transfer occurs. Please, are we following? Good. Now let's look at what HOMO actually means. Now, as we said, highest occupied molecular orbital. So now you know which of the molecular orbitals are the occupied ones, and then you know which ones are the unoccupied ones, right? So because we are talking about highest occupied molecular orbitals, it means that for HOMO, your attention should be on the occupied levels, right? So we come to the occupied levels, which is the n, the pi, and then the sigma. These are the levels we are considering in terms of occupied molecular orbitals, right? But then among these three, which one has the highest energy? That is what you have to consider. Follow the cursor very well. Sorry, that's funny. Follow the cursor very well, and then you see. Look at the energy bar. This big arrow pointing upwards is the energy level. All right. So from down to top, that is how the energy increases. The bottom of the arrow is the lowest energy, and then the tip of the arrow is the highest energy, right? So in order to identify the highest occupied molecular orbital among the occupied levels, you follow the energy bar and you realize that the non-bonding molecular orbital, which is the n, is what represents the HOMO. That is the one that is having the highest amount of energy among the occupied levels, right? So when we are considering the HOMO over here, the HOMO is the n, then the non-bonding molecular orbital for this particular molecular orbital diagram. Please, are we following? Good. So if you understand that very well, then let's look at what the LUMO means. LUMO is the lowest unoccupied molecular orbital. So once you hear unoccupied, it means that you have to come to the unoccupied levels, right? The unoccupied level consists of the pi star and then the sigma star. Okay. Now among these two, which one has the lowest energy? It's obvious that it is the pi star, right? Good. So here our LUMO is the pi star and our HOMO is the n, right? So for us to be able to understand what HOMO to LUMO electronic transition means, as the subtopic indicates, It is what the transfer of electron or the jump of electron from this level, from the n orbital to the pi star orbital. So if an electron is able to jump from here to here, then we refer to that kind of transition as what? A HOMO to LUMO electronic transition. Please have a follow. Good. If you understand this perfectly, then let's look at the third point. What does it say? It says that the electron transition with the least energy, often observed using UV light, usually involves an electron moving from HOMO to LUMO. So we said that you could see that the gap between the n and then the pi star is very small as compared to the other ones, right? So it's very obvious that this particular transition is the one that has the lowest energy, right? Good. So we say that what the lowest energy transition, which is this HOMO to LUMO, is the one that is usually observed. It doesn't mean that the other ones are not observed. No, the other ones can be observed under the right conditions, but the one that is typically observed or typically known or seen in visible spectroscopy is the HOMO to LUMO, which is the movement of electron from the n, the non-bonding orbital, towards the pi anti-bonding orbital. Please, are we good? Right. Let's move on to the next slide. So let's look at typical examples of how the electrons are transitioned. Okay, so for example, if we take a hydrogen molecule, hydrogen gas, for example, we are combining two atoms of what? A hydrogen to form a hydrogen molecule, right? Good. So you can see that from this particular diagram, we only have sigma bonds. We have the sigma bond here, and we have the sigma anti-bonding orbital over here, right? So here you don't have an option to select between your to select which is LUMO and which is HOMO. It is obvious that this will be our HOMO. Why? Because it is the only occupied molecular orbital that we have here, and then this is the only unoccupied molecular orbital that we have here. So this is going to be our LUMO, and this is going to be our HOMO, right? So if an electron is able to jump from the HOMO to this LUMO, then we say that a HOMO to LUMO electronic transition has occurred. All right, good. From the previous episodes, I explained that for an electron to be able to make a jump from one orbital to a higher energy level orbital, it should be able to absorb or gain some amount of energy that is required for that particular jump, right? So, for example, you could see that the jump from here to here, look at the energy gap, look at the arrow. This energy gap is what? It requires 258 kilocal per watt mole, right? So in order for this whether red or pink electron to jump from its recent position to the LUMO position, it requires this amount of energy. All right, so how does the electron get that amount of energy? We give that amount of energy to the electron by what? Exposing the electron to what? A UV light and an ultraviolet radiation. Okay, now the ultraviolet radiation that we have to expose to this electron must have this amount of energy, so that once the electron absorbs the light, it will be able to what? Gain that amount of energy to make the jump. Okay, so you realize that the corresponding wavelength of a particular UV light that contains this amount of energy is 111 nanometers, right? So this wavelength of light is what contains this amount of energy that will enable this pink electron to jump towards the LUMO position, right? So once we expose this electron to this amount of UV light, you realize that it will gain the energy that will enable it to jump. So as a result, you realize that the electron will finally jump towards the unoccupied position. Okay, and then you'll be able to calculate or find out the amount of energy that the electron absorbed when you analyze your absorption spectrum, as I explained in the previous episode. Okay, so the same thing applies to the second example, ethene. This is an alkene group. So as I explained in the first example, it requires what? This electron, for the electron to jump from this HOMO to LUMO. You could see that this HOMO to LUMO is now pi to pi star. It is no more what? Sigma to sigma star. Why? Because this particular compound is different from this particular what? Compound, or this particular molecule is different from this particular molecule. So the HOMO to LUMO transition varies. It can be sigma to sigma, it can be pi to pi, it can be n to sigma, it can be n to pi star. Please, are you following? Good. So it is not strict or it's not specific or chinchina that the HOMO to LUMO transition is always from N to pi star. No, no, no. It can also be from sigma to sigma star, or it can also be from what, pi to pi star, depending on what the molecule or the sample that you are dealing with. Please have you followed? Because all samples or all molecules cannot have the same molecular orbital diagram. Good. So following the same explanation, you'll be able to explain that of the 18. So let me give you a short exercise. You can pause the video and try to explain this particular example to yourself. Try to see if you'll be able to understand what this particular diagram means. Imagine if your friend comes to you and asks you that, oh Charlie, explain this particular thing for me. What does this whole thing mean? What does it mean? Try to see if you'll be able to do that job. Okay, so we just pause the video. Try to see if you'll be able to explain it to that your friend. All right, if you get it wrong, just go back to the aspect where I use the first example to do the explanation, and then you get the understanding, then you can come back and try it. Okay, so now let's move on to the next slide. What do we have here? Here we are going to talk about the major organic functionalities and their respective electronic transitions. So starting with this, you know, in organic chemistry there are several functional groups. We have alkanes, alkynes, carbonyl groups, halogens, a whole lot of them, right? But then we are just going to tackle these major ones. Okay, every sample that you are going to analyze might one way or the other contain any of this. It might not contain all, it might contain a combination of some of them, or maybe a single quantity of one of it. Okay, so maybe I'm analyzing a particular compound or a particular sample that contains organic functionalities like alkanes and then carbonyls. You realize that combining alkanes and carbonyls, then it means I'm going to be observing like two different kind of transitions or electronic transitions, right? Good. So I want to expose you guys to this particular group of compounds and then their respective electronic transitions, because most of the compounds or molecules that you are going to be analyzing will contain what these functional groups. Okay, so as I explained earlier on, now you'll be able to boldly point out which one is the HOMO and which one is the LUMO, right? Good. Now you could see that we said that alkanes, usually we see this kind of sigma to sigma star electronic transition. So this is the electronic transition that usually occurs in alkanes. When it comes to carbonyls, it's sigma towards pi star. When it comes to unsaturated compounds, when we say unsaturated compounds, compounds that usually have multiple bonds like alkenes, alkynes, okay, yeah, this kind of compounds, you have pi to pi star transition as they are what, HOMO to LUMO. Okay, and then here we also have the N to sigma star. That is for compounds that contains oxygen, nitrogen, sulfur, and then halogens. When we talk about halogens, I think you are familiar with that. The group 7 elements, the chlorines, the fluorines, the bromines, and co. Yeah. And then when we talk about carbonyls again, you realize that we also have another N to pi star. So you see that carbonyls has occurred twice here. We have a particular carbonyl that you can see sigma to pi star electronic transition over there. And we also have a carbonyl that you can see N to pi star electronic transition over there. Okay, good. So let me give a typical example for you to understand what I'm trying to say. So for example, let's say let's use the same example that I used in the second episode. I said earlier on that should in case your supervisor gives you a particular liquid that you don't know anything about, is plain, you don't know the content, and then he wants you to characterize the solution that he has given you. Let's say the solution contains alkanes, okay, but you don't know. If you run your spec and then after your analysis and you realize that, oh, the electronic transition that really occurred, or the kind of UV light that was absorbed, okay, as a result of you getting a particular absorption spectrum, is corresponding to this particular electronic transition, that is sigma to sigma star, then you're able to see that, okay, this particular liquid that my supervisor gave me contains what, an alkane. Okay, but if you check and then maybe it corresponds with an electronic transition that involves N to sigma star, then you might conclude that the the solution given to you might contain an oxygen molecule, a nitrogen atom, sulfur, or any of the halogens. Okay, so this is the very reason why we want you to get these connections. This is what will help you understand or characterize a particular compound. Okay, let's move on to the next slide. Now let's look at the meaning of far UV, near UV, and vacuum UV. What does it mean? When someone asks you what is the meaning of far UV, how do you explain to the person? So let's see what we have here. Far UV typically refers to wavelengths in the UV region that extend from 91 to 200 nanometers. Okay, so this wavelength 91 to 200 nanometers is not fixed. Okay, some sources, I mean some books or articles might give you slightly different, maybe plus or minus some slight values that might be slightly lower or higher than the range that I've given over here. But then this particular content is just to make you get the idea, the understanding, okay, of what or where to head to in case you are thinking about far UV, or what you think, like what you need to think about, the region on the electromagnetic spectrum that you need to look at in terms of what far UV. Okay, so don't necessarily mold these values, don't mold them for you to use in exams or something, but it will give you the idea that okay, when we talk about far UV, it means that it involves the UV radiations that have the lower wavelength or the smaller wavelength, something like that. I hope you get what I'm trying to say. Good. I'm sure if your lecturer is taking you through a course like this, he or she would definitely give you specific values that he would want you to use, but this is just to give you the idea of what far UV means. So come to the diagram, follow the cursor. You could see that this violet bar from here, this rectangle from here to here, the UV region is what spans from 100 to 350, as I spoke about in the previous episodes. But we are saying that when we say far UV, it means that the radiations that are close to the X-rays, all right, that is roughly from 91 to 200 nanometers. So you realize that far UV radiations usually have small wavelength as compared to the vacuum UV and the near UV. Okay, the vacuum UV also is in the same range with the far UV, just that there is a slight difference. Some books will clearly differentiate them, and some will use them interchangeably. So sometimes we refer to far UV as vacuum UV. Yeah, some sources will say far UV or vacuum UV, but then the idea is that when we say far or vacuum UV, it means that these radiations are in the UV region, but then still in the UV region there are categories. So the radiations that are of lower or smaller wavelength in the UV region are the ones that we call far or what vacuum UV. Okay, talking about near UV are those, obviously, are those that are having the big wavelength in the UV column. So you can see that it says that what near UV region, which is closest to visible light, encompasses wavelength ranging from what 200 to 350 nanometers. Yeah, so these ones are close to the visible light, they are close to the visible region, they have long wavelength as compared to the far or vacuum UV. Please, I hope you get it very well. So when you go to your exams or quiz or an interview and they ask you explain to us what far UV or near UV means, I hope you're able to ace that. Thank you very much. Let's move on to the next slide. I think this is the last but not the least slide. Let's look at why some electronic transitions are observed and some are not. Okay, so as I said earlier on, electronic transitions, there are several of them that are possible. Okay, but then it is not all of them that are observed. All right, so why is that? Why is it like that? Let's look at what we have here. The first point says that oxygen in the atmosphere absorbs UV radiation of wavelength less than 200 nanometers. So the first sentence is that when you have a wavelength that is below 200 nanometers, oxygen will be able to absorb them. Okay, so if oxygen is absorbing them, it means that the radiation will not be able to successfully get to where you want it to get to. Do you get it? We said what? Why does oxygen absorb this radiation? It is because the electrons in oxygen molecule require such short wavelengths in order to undergo what? Electronic transition. Hence, oxygen becomes increasingly non-transparent below 200 nanometers. So this particular point is talking about the fact that oxygen requires ultraviolet radiations that are below 200 nanometers in order to undergo electronic transitions. Okay, so when you use such radiations, radiations that are below 200 nanometers, when you use them, oxygen will end up with interfering with your results. For example, let's say I want to expose a radiation that has a wavelength of 150 nanometers to a particular sample. Okay, and then don't forget oxygen is in the air, right? So wherever you go, unless you are working in vacuum, okay, if you are working in an oxygen rich environment, a place where air can reach, it means that oxygen can also reach there. So before the radiation would travel through air and enter my sample for my sample to absorb it, oxygen will end up with absorbing the radiation before it even attempts to enter our sample, right? So the kind of electronic transition that we expect to see in our sample will not be visible because it will not occur. Why? Because the radiation that was supposed to go and give the electrons within your sample the amount of energy, or that exact amount of energy that they need in order to do the transition, will not get there. Why? Because oxygen will end up with absorbing such a radiation for its own electronic transition. Okay, so when that happens, you are not able to observe or see the electronic transition occurring within your sample. Rather, it occurs within oxygen. Do you understand it? That is why we say that oxygen is not what transparent below 200 nanometers. What is transparency? If something is transparent, it means that electromagnetic radiations such as light should be able to pass through it, right? Okay, but then here we are saying oxygen is not transparent. It means that it does not allow such wavelengths below 200 nanometers to pass through them. Rather, it ends up absorbing such radiations. So when you are working in an environment where there is definitely air, then you need to be able to understand or critically look at the kind of wavelength you are working with. So far as it is below 200 nanometers, you wouldn't be able to get the accurate result. And when you end up working with such results, you end up making wrong conclusions and then giving wrong suggestions. Yes. The second point says that in order to study UV radiations below 200 nanometers, special equipment to study vacuum or far UV is required. So now I know that if you actually followed the video very well, you would have understood what vacuum and far UV means. It means that radiations that are below 200 nanometers, radiations that are close to the X-ray region, right? Radiations that are below 200 nanometers. Is that not it? Good. So we say that in order for us to be able to study such radiations, we need what? Vacuum or far UV equipment that are designed specially to study such radiations. How? It means that in order for you to be able to study such radiations that have wavelength below 200 nanometers, you should be able to what? Exclude air in the environment. So it means that definitely you have to work under what? Or you have to work in what? In a vacuum condition where there is no air, there is nothing. Please, are you following? Good. So with this explanation, I'm sure you now understand why some electronic transitions are not observed. Thank you very much for watching the video. I'm very grateful. Let's look at what the last thing has to offer. So for the final part of the slide, we have examples of electronic transitions over here with their specific wavelengths. And as I said, if it is below 200, you wouldn't be able to observe them. So the ones that are in the, will I say, colored rectangle, those are the ones that are not observable. Why? Because you could see that it's obvious that they are below 200 nanometers, right? Now you ask yourself, why is it that this particular one, the pi to pi star transition that belongs to the unsaturated compounds, which has a wavelength of 180 nanometers, still observable? It is observable because you can see the condition over here. We say what? If they are conjugated. Okay, so conjugation plays an important role in UV visible spectroscopy, and then we are going to look at it in subsequent videos. All right. Today I wouldn't want to tackle it because it might bring confusion, but then I will definitely tackle it as we proceed. Okay, good. So if a particular compound is conjugated, you would be able to visualize or see the electronic transition. Why? Because conjugation helps to increase wavelength. Okay, just keep that in mind, that conjugation helps to increase wavelength. So if a particular compound is conjugated, then you'll be able to observe its electronic transition. That is why even though this one is 180, if we conjugate it, it will become what? Visible. Okay. Then we can look at that of the carbonyls from N to pi star. It's obvious, 300 nanometers. It is way above 200 nanometers. So you'll be able to observe such an electronic transition as well. Alright, so these are some of the references, some sources that I picked some of my information from. You can go through them should in case you want to. Thank you very much for watching the video. I'm really grateful. Um, just for the fact that you're able to stay from the beginning of the video till now, it means that you are really serious and you want to get in-depth understanding of all the things that are involved in UV visible spectroscopy. And I promise you that I'm definitely going to deliver, and I'll make sure you get all the understanding that you need. Just make sure you subscribe to the channel, like the videos, and share them for your friends to also benefit from what you are enjoying. All right, and also don't worry, the subsequent videos are going to give you more understanding and also going to open your eye on some things that you might not have heard before, and then it will help you enrich your understanding in the field of analytical biochemistry, or specifically in the field of UV visible spectroscopy. Thank you so much for watching the video. I'll see you in the next episode. Bye bye.